Plastics are synthetic polymers. We've looked at the addition polymerization reaction that takes monomer starting material. Those are the individual molecules, and bonding together to form the synthetic polymer, which is just the monomer over and over and over again. Typically for the addition polymerization of the common everyday plastics, it's the same monomer, but we also mentioned the most common plastic number one is two different monomers. It's going to end up a very large molecule called a macromolecule. So in comparison to the compounds we've talked about so far, which are ionic compounds and covalent compounds, those are just a handful of atoms. Well, these polymers become hundreds, thousands, millions of atoms that are represented in the overall bonded polymer. So we'll get into biological macromolecules, which are still giant molecules, hundreds, thousands, millions of atoms. Some of these you've heard of in foods. We'll get into in chapter 11, carbohydrates, proteins, and lipids in foods. And in chapter 12, we'll talk about the hereditary material in humans, DNA and RNA. All of these are biological macromolecules that are polymers. These are examples of just 3 of the 60,000 synthetic polymers that we come across in our everyday lives. So the monomers are bonded together over and over in the addition polymerization reaction, and we talked about the ethylene monomer. So the ethylene monomer has 2 carbons with the double bond and 4 hydrogens. Breaking the double bond allows for bonding of one monomer at a time to one side of the growing polymer chain. In what way are these 3 monomers similar to ethylene? So we can see that these 3 monomers, though this has 4 fluorines, this has 2 chlorines, and this has 1 chlorine, what they all have in common is they all have that double bond. So how are these different? Well, some of these have the hydrogen replaced by a different atom. Okay, so is it all of them, or chlorine, or one or more hydrogen replaced by a different atom? So these polymers, let's start with this polyvinyl chloride. Putting together these monomers requires breaking the double bond of the monomer, and this allows for addition of the new monomer to just one side. And each monomer that's added, the double bond breaks and is added to one side of the growing polymer chain. Now I'll try to add this next monomer to this side, to the left side. Okay, so on the left side, what happened? It wasn't allowed. This side, in theory, has a catalyst attached to it, and the growing polymer chain always adds to one side in the addition polymerization. So I'll show you again. I'm trying to add it to the left side, and it instead adds to the right side. So the overall chemical equation is that there were 5 monomers, and that the polymer is shown as a bracket, and that you have this same monomer over and over 5 times. Now this is a subscript, and the larger polymer would contain a lot more than 5. However many, in the thousands, depending on the reaction, how many monomers you start with, will all go into the polymer.